some idea. And again, I will be giving this as a handout, and I will be also giving a tutorial problem. That's my bad habit. So that at least you carry something beyond when you go back from Hyderabad to, say, Trichy, at least you have something to fall back on. Okay. First, the wind, then the earthquake, and then a little bit of the computer-aided analysis because hand calculations is not possible. That's why some idea about how you approach it. Now, what are the reference material? Now, this particular book, Pillai and Devdas Menon, this is a very good book on the reinforced concrete design, which also covers this basics of seismic and wind. That's why I would say, at least for the undergraduate students, please get this book and get familiar. The codes 875 part 3 is for the wind, 1893-2016, which has been recently revised, but I will be covering 2016 only. 4326 is related with simpler buildings like small multi-story buildings. 13920 is related with the ductile detailing. 15498 is related with, again, simple buildings for the cyclone resistance. SP34 is a generic handbook detailing. We should be familiar with.
What does the SP stand for, sir?
Special publication. From the Bureau of It is from Bureau of Indian Standards. Yes, yes. It is a must for a practicing engineer. Whoever works with reinforced concrete should be familiar with this. Now, coming to wind. See, many of the times our engineers have the wrong conception that if we design a building for gravity loads, and this wrong conception can be very treacherous for precast buildings. But if I am designing for gravity loads, since there are safety factors, it will take care of lateral loads. No. Safety factors are not to cater to this lateral load. Safety factors are to cater for the material variability and the variability in our modeling. Wind load is primarily a horizontal direction. That means now we are talking of a different direction of loading. Till yesterday we were talking of only gravity loads. But today we will be covering loads which are in the horizontal direction. And hence a structure needs to have proper lateral load resistance. Okay. It is dynamic in nature. Unlike gravity, which is constant every second, wind varies. And whenever there is a dynamic load, we have to fall back to the structural dynamic concepts which we learn in basic physics, like frequency of vibration, amplitude of vibration. All this becomes consideration. It is reversible in nature. Gravity is never a reversible load. Okay. Had it been reversible, I think Earth would not have been habitable. Okay. But wind is a reversible load. Okay. It depends on the location of the Earth. See, gravity slightly changes if you go up, but that is disregarded in structural design. Okay. But wind, it very much depends on where you are. It also depends on the height of the ground, the terrain conditions, and the topography, and you can understand the complication that is becoming. Okay. And a very important thing, it is uncertain in nature, unlike gravity. Now, in this presentation, what I'm covering is, wind can be a whole course, semester-long course, but I'm just covering in half an hour wind. We are just covering the determination of the external forces acting on the building as a whole. I'm not treating you how to analyze facade elements, which is a part of precast buildings. You have to know, if you're designing facade elements, how to treat those non-structural components. We're not talking about that. Now, whenever we are doing wind analysis, first we can treat the whole building as a whole. That is called a system level analysis. That's what I'm briefly covering today. But then There can be component level analysis, as I said, especially for lightweight roofs, for facade elements, for glass panes. This becomes, in fact, the second becomes even more important because they can be falling hazards. Now, for the wind, there can be different levels of sophistication of analysis. The one that I am covering today is the equivalent static analysis. That means all this dynamic thing, we are saying that no, we will be doing a static analysis, but hopefully that will give a conservative result. But there can be dynamic analysis for bridges or tall buildings that is done, and experimental methods, the wind tunnel tests. Okay. I am just covering the first one as per IS 875 part 3. Now, what are the steps that let's be prescriptive in nature right now? We are not going to the theory, we are just going to know how to do it. That first of all, since it depends on the location where you are talking about, you have to have a wind zone map. From there, you get a quantity which is called a basic wind speed. That value, the anemometer, from the anemometer readings, people have come up with a certain return period, and there are different what is called averaging techniques based on that. Some with some probability, they come up with a basic wind speed data at a certain location. Then you have to design from the wind speed, basic wind speed, you have to get a design wind speed which considers some other variables. What is the height I am talking about? Okay, now what are the ground conditions? Is it an open space? All these things comes up with certain factors that from the basic, with those factors we get the design wind speed. From the speed, we get pressure. And here this is based on the Bernoulli's, some theories there, but the code gives a very straightforward approach that from the speed you get a pressure on the area which is obstructing the wind flow. From the pressure, you calculate the load at a certain level. Typically what we do is, whenever we do a building analysis, we lump the masses at certain heights. It's a discrete model, it's not a continuous model. However, for a tall building, you can do a continuous model, but otherwise we typically go for a discrete model. That means the masses are lumped at certain levels, and in those levels we apply the forces. That means whatever pressure comes in the area obstructed, based on a tributary area at a certain level, we calculate the force. And once we know the force, the subsequent thing is the structural analysis, which is done using a computational model. But up to here, either you do it by hand, or these days sometimes the programs can do it for you. But I would say, as a student, we should know how to calculate these forces which I'm using to analyze the structure. That I should be knowing how to do it by hand. The basic wind speed comes from this wind zone map. Now there are certain adjectives here. This wind zone map is based on a peak gust velocity of wind for a return period of 50 years. Why 50 years? That this is our thumb rule design of a building life. That we typically design a building for 50 years. That's why that is the convention. And that is given at a height of 10 meters from the ground level. Anything below the 10 meters, we say that let's forget the variations. There is a lot of, there can be undulations, and we don't worry about the variations within the 10 meters. Whatever is given in the 10 meters is considered that it is constant in the lower 10 meters. However, if I am going above 10 meters a building, then I have to go for with increased values, which comes through some factors. The following zone map is what we have in India. That means this is the map. If I now look into the values that this particular region, which is this part, which is having 55 meters per second basic wind speed. Okay, I'm just giving you some values. This whole coastal area, which is the cyclonic area. Okay, when Chennai falls here, the wind speed is 50 meters per second. If I look into Hyderabad, Hyderabad falls somewhere here. This is 44 meters per second. This is the leeward side of the Western Ghats, much less. Okay, this is the least we have. Roughly, this is the way our wind zone map is. That means if I'm in this coast or in this coast, that is a very high. This is a very hilly terrain, that's why it is extremely high. Whereas in this portion, wind design is not a concern unless the building is very tall. Okay. Now, from the basic wind speed, that means we are getting the value from that map for the place where I'm designing the building. Next, given that value, I'm multiplying by certain coefficients. The first coefficient is a risk coefficient. And see, I'm telling this to Josepha that if you look into the International Building Code, the expression may be slightly different, but the concepts are same. Because today, if you're learning this one, it will be easy for you to pick up other international codes. Okay. K1 is called a risk coefficient, that if I'm designing a building more important, okay, targeting a life more than 50 years, then I should boost up. K2 is the terrain and height multiplier. That means if I am going for a tall building, again I have to boost up the pressure, speed. K3 is a topography factor. That means what, say if I'm in a very, say if I'm in the valley region, okay, say Araku Valley, which is a very nice place close by, then whatever happens in the valley and whatever is happening in the crest will be different. Okay. And K4 is an importance factor specifically applied for a cyclonic region. Now this is typically for cyclone shelters which are to be functional even during any, after any major cyclonic events. The whole East Coast is subjected to cyclone. There are several cyclonic shelters. For those type of buildings, this K4 factor is used, this has been introduced in the latest version of the code. Now that means there are tables given in the code from where we can get these factors and come with the design wind speed. That means from the basic wind speed, I'm getting the design wind speed. Then this expression is based on Bernoulli's principle that from the design wind speed at a certain level, I get my pressure. Please note these are all unit dependent and this pressure is in Newton per meter square. Okay. And this particular coefficient is an average coefficient for Indian conditions. Now, if I am designing specifically for cyclones, as I said, that's more for special buildings, then there is something called directionality effect. But right now, let's not worry about that. Whatever is the orthogonal directions of a building, we typically analyze in those two directions. But now if we say, no, the wind is coming from some other direction, then we have to worry about that if that building is a special type building.
So this windrows diagram is a standard diagram in the blueprints?
No, windrows diagram is not given in the code. Based on the windrows diagram, the directionality factor has been given. But directionality factor is used only for, as I said, special buildings, not for conventional buildings. Now in the system level analysis, now what we are doing is whenever we are developing the model, we are first identifying the different heights of the levels. Typically those heights are the floor levels, which we get from the architect's drawing. And for those different levels, I am calculating the velocity. If the building is small, a few storied, which comes within 10 meters, that means the velocity is same throughout. But if the building is tall, then above 10 meters, my velocity increases. Now given the velocity, if the velocity increases, obviously the pressure will also increase. And to the pressure, we are multiplying the effective frontal area. What it means is that if a building is curved, then I just take the projected area which is perpendicular to the direction of the wind flow. Like that, I calculate my effective frontal area. And CF is a coefficient which depends upon the building geometry. Now, again, there are several charts. If the building is more industrial type, then those charts become a bit more involved. But for conventional rectangular block type of buildings, the value of CF can be found out from a diagram this is the simplest diagram, that this is applicable for a building which is like a rectangular in elevation and rectangular in plan. Then depending upon the aspect ratios in elevation and the aspect ratio in plan, we can get the value of CF. You can understand that this itself gives you some idea that depending upon certain geometry, the CF will be low, whereas for certain geometry, the CF can be very high. Okay. Why this happens is there are effects called what is called the formation of vortices behind the obstruction, and based on that they have come up with these coefficients. Now if I do a component level analysis, then my expression is a bit different. In the component level analysis, what happens is, apart from the obstruction, there is also a suction effect. That means since it depends upon how much the wind can blow. Today I have a glass pane here, and if I'm designing this glass pane, there will be a wind coming from the front, but then there can be also having a suction effect depending upon how much wind can flow. And hence, the expression has CPE, which is the external pressure coefficient, and internal pressure coefficient will be negative. Negative becomes positive, as essentially the external effect and the internal effect becomes additive. Okay. Now this is something which we have to worry about if we are analyzing in a component level like facades or lightweight roofs, then we have to worry about this. But right now I'm not going into that. Okay. The value of CPI, this internal pressure coefficient, depends on the area of the openings in the walls. Because in this room, how much opening is there, based on that, this CPI coefficient has to be determined. Now let's come back to the system level. The system level, the way we idealize a building is that from the ground level, finished ground level, we are first calculating the heights of the different levels. Again, that comes from the architecture drawing. That means I know this height. From the height, I know the design wind speed. From the wind speed, I know the pressure. From the pressure, with the area times some coefficient gives me the force. What is that area? Area is the width of obstruction times the tributary height. That means, say for the roof, the tributary height will be from the mid height of the top story to the top. For any other level, it will be mid height of the upper story to the mid height of the lower story. That is my tributary height. That means tributary height times the width is my effective area. Okay. That means what I tell my students is that given and this is your tutorial today, that given the force, given starting from the basic wind speed, can I come up with this values of the force? That will be the tutorial problem. From here onwards, it is a structural analysis. Now, even before jumping into a structural analysis, I tell to the students that conceive the building as just a stick model. What is a stick model? That means I am forgetting the two-dimensional distribution of the floor. I am thinking as if it is lumped at one point, and I am just interested in the vertical distribution. The idea about the stick model is to see what is going to happen due to the vertical distribution. So these are lateral forces acting at different heights. The summation of these forces creates what is called the base shear. The base shear is the important quantity of any lateral force. Next, when we come to the earthquake, it will be even more important. And another important issue is what is called the overturning moment. What is the overturning moment? On the foundation, see, please note here I have used the heights from the top of the foundation, not these values. The overturning moment on the foundation is each force times the respective height. You take the cumulative effect, that is the overturning moment. That means as a designer, you don't jump into a building analysis right away. First, you do this small hand computations, jot it down in your notebook, get a feel that how much force are you applying onto this building. Then you use these values to do your structural analysis. Okay. How do you do? I tell the students that you should always do this in a neatly, because when you're a practicing engineer, see, sometimes our students think, okay, I can submit some homework. If it is not good, the teacher will deduct some marks. I don't care. But I said that in a practice, you're going to do like that. In a practice, whatever design sheets you're having, you may be getting that from the company and you feel very happy that you're getting free stationery. Unfortunately, those are all archived. Who knows, 30 years down the road, those sheets may be pulled out just to check whether this building is still adequate or not. And hence, you should record. So you don't have the privilege to type everything. You have to do it by hand. And very neatly, you can do a tabular calculation that for the different levels, I'm calculating the heights from the ground level, I'm calculating the height from the top of the foundation, I am getting this K2 factor. K2 factor depends on the height. I'm getting the design velocity, the pressure, I'm calculating the area for each level, and I'm calculating the force. And I'm calculating how much it contributes to the overturning moment. The summation of the force is the base shear, the summation of all this is the total overturning moment. This will be your exercise for the tutorial. Okay, I just want this table. Next, this is the analysis for wind. That means you're calculating the wind forces, then you may be having a computational model where you're applying the force and the model will give you the internal stress resultants, which is the bending moment, shear force, axial force. Now once you get those, then you are designing the building. Now what are the issues of wind design? First of all, this particular code, IS 15498, gives certain guidelines. Now comes the detailing aspect. Design means an important aspect is the detailing. Okay. But for a lightweight roof, especially for industrial sheds, this becomes a concern that will be blown off. You go to a place like Vizag and this tornado comes, they can be blown off. That's why there are provisions, there are specifications, I would say, for adequate hold down devices and providing horizontal braces at the tie level. I'm just raising these issues. Later on, if you are working, then you should read this code and get familiar with the specifications. For mid to high-rise buildings, there should be adequate resistance for the lateral loads in terms of stiffness and strength. For low-rise buildings, I'm not talking of the system as a whole. It is not the issue. The issue is with the roofs. But whenever I'm talking of mid to high-rise buildings, first I have to look at the system as a whole. Then I have to look into the facades. Okay, the design part, the detailing specifications, I'm not going further. Next comes the earthquake forces. Now, earthquake force is not a true force. It is an inertial effect. What it means is there's a ground shaking, and since the masses of the buildings cannot move simultaneously, they fall back, and that's why there is a relative displacement between the different levels, which generates internal forces in the supporting members. Okay. Now, the earthquake primarily acts in the horizontal direction. The first you analyze for horizontal directions. Now again, for a building, whenever we design, we typically identify two orthogonal directions, X and Y, and we design the earthquake for those two directions, although the earthquake can come in any other direction. There can be vertical component also, but I'm not referring to that right now. Again, earthquake is also dynamic in nature. And as I said, that amplitude, frequency are an issue. It is also reversible, like wind. It also depends on the location of the earth. That's why we have seismic zone map. Earthquake depends on the type and deformation of soil. Now this is very interesting. In wind analysis, our geotechnical folks are never involved. Okay. Whereas when it comes to earthquake design, we are heavily involved with our geotechnical friends. With their data only, we has to start with. I will tell you where it comes. And another very important difference with wind and earthquake is typically we design wind to stay elastic. Okay, that under the design wind force, the structure will stay elastic because we can afford to do that. Whereas for earthquake, the forces are so high that even for the design wind force for conventional buildings, we cannot afford to have the members stay elastic. Then we have to design it as a nonlinear behavior because otherwise it will be very costly. Okay. And earthquake is also uncertain, and hence all this probabilistic approach comes in earthquake also. Just like wind, we have different methods of earthquake analysis. The simplest one is the equivalent static method, where the inertial forces are treated like as if physical forces acting at different levels. Please note, this is an idealization. Okay, that someone has done this structural analysis, or I would say structural dynamics. From the inertial effect, we are trying to get these forces as if they are physically statically acting. Conventionally, we neglect the nonlinear deformation. And how do we account for that? I will come to it later. The next level of analysis is the dynamic analysis. One method is called the response spectrum method, where we account for the different modes of vibration of a building, especially if a building is atypical, then we go for the response spectrum. Or there is a time history analysis, which is like solving a set of differential equations which are with respect to time. If you're going for the nonlinear behavior of the materials in our analysis itself, then that method in a static form is called the pushover analysis. This is becoming more and more common even in the practicing engineers, because you can have a more economical design if you are going for a pushover analysis, provided we justify with the connections. Okay. The nonlinear dynamic analysis means which is related with the time-wise variation. This is more within an academic circle. And we can also have experimental method which is based on shake table tests. Now here I am just covering the equivalent static method as per IS 1893. Now this is a shake table we have in our lab. I am just throwing a picture from our lab that our steel students mostly use this shake table. Also our masonry students, depending on the payload. Payload means the load that it can carry. We cannot do concrete specimens here, but this type of rack structures or masonry structures can be done in this type of shake table. Now the equivalent static method, the way I am following as per the 2016 code, okay, because 2025 it is yet to percolate down. The way the static forces are computed is that first we compute the summation of these lateral forces, which is called the base shear. Okay. The base shear is given as a certain coefficient times the weight of the building. Now please note, this is another difference with the wind. In the wind, the major aspect is the effective area of obstruction. And if I am having curved buildings, my coefficient comes down and I get some benefit. Okay. For the earthquake, it is the mass of the building which is more important. If I can reduce the mass, okay, then my earthquake force will come down. That means mass times the acceleration due to gravity is the weight, times some horizontal coefficient is the total of the lateral forces. Now this coefficient is given as first a factor which is based on the seismic zone. This is where we take account of what is happening in the different locations in the earth. This by 2 is to have what is called from the design basis. I mean, for conventional buildings, as I said, that we cannot afford to have the force at Z, we divide it by 2 But we have to be careful that we have to have ductile detailing. That's where the importance of connection comes. If we have ductile detailing, then we can reduce this to half. Okay. I is an importance factor depending upon if you are doing a hostel building, housing 500 or 1000 students, definitely that I factor will be higher. R is called a response reduction factor. Now this is where we are considering the nonlinear deformation of the structure. That we are doing a linear analysis, but in reality for those forces, actually the structure will become nonlinear. Let me just quickly draw and this is a schematic representation of, say, a building like a single degree of freedom system. As if V is the total force and delta is what is called the drift of the roof. My analysis states it's a linear analysis. I will be getting a result somewhat like this. That is, given a certain base shear, my roof displacement will increase linearly. But in reality, it is actually like this. Okay. And this reduction is taken care of by this factor R. Now, how much it will reduce depends on how much ductility are you incorporating within the system. And that's why our code gives us this option that you can go for reduced forces, more and more reduced forces, but then you have to put the price by having more stringent detailing conditions so that you can maintain the ductility as a system. Okay. Now, given this, this quantity, SA by G. SA by G is called the spectral acceleration. I will come to that a bit later, just hold on to it. Now, what is this weight? This total weight is the summation of the weights of individual levels. That's it. Okay, this slide just explains whatever I said. Now, coming to the zone factor, in the 2016 code, the country was divided into 4 zones, and corresponding to each zone, this was the factor. You can just think in a simple terms that as if the horizontal acceleration is about 10% of the gravity. That's the way you can think, okay, which was in Hyderabad. If I go to Chennai, which is in zone 3, it is about 16% of G. If I go to zone 4, say Delhi or Mumbai, then it is 24%. If I go to a place like Guwahati, it is about 36% of the acceleration due to gravity. Now this is the zone map in 2016. What are the 4 zones? That Hyderabad falls here, which is zone 2. There is no zone 1. Earlier there used to be zone 1, but zone 1 has been removed. Zone 3, zone 4, okay, and these are zone 5. Now this map has got substantially changed in this latest version of 1893. Now what is the main difference was the previous map was based on recorded data. Okay, whatever recorded data we had from over the last maybe 100 plus years, based on that it was made. But now a new method has developed which is called probabilistic seismic hazard analysis. Based on that, because that is not just the recorded data, but they also study the geotechnical conditions, and based on that they come up with this map. Lot of work has been done to come up with this map which is based on a probability that in future this may happen with a certain probability. And what we see the main difference is now a new zone has been added, which is zone 6. Okay. Zone 6, most of our Himalayan region, which is actually highly susceptible. Okay. Places like Nainital, anything can happen anytime. Okay. Along with that comes landslides and all associated things. Now this is zone 6. Hyderabad is still in zone 2. Okay. Not much to worry about the change in the code. But there is another important thing which has been brought out in this code is that you have to now select appropriate return periods of the earthquake. Till the previous code, our return period was considered to be 475 years. 475 years is related with a certain probability of occurrence within the 50-year life of a building. But now for important buildings, now when I'm coming from airport to here, there are so huge buildings in Hyderabad. That means for those buildings, your return period should be higher. And what happens is, even if Hyderabad is in zone 2, for those super tall buildings, you have to design for much higher earthquake forces. Maybe which is more than even some lower buildings in zone 3. That's where definitely this earthquake design will become more stringent with this present code compared to what we are having till now. Okay, let me go back to again going back to 2016, that the importance factor for any lifeline buildings is 1.5. For residential commercial buildings with occupancy more than 200 is 1.2. Rest of the buildings I equal to 1. Coming back to the R value, we broadly classify the concrete buildings into two groups. One is called the ordinary moment resisting frame. Ordinary moment resisting frame means where we are at least satisfying the requirements of the gravity load design, IS 456. Even IS 456 also has a minimum ductility requirement. Please note, we always have to design as under reinforced. For that type of design, R should be 3. That is the conservative value. But in case if you are going for special detailing, then it is called specially designed moment resisting frame, SMRF. The other one acronym is OMRF. Then we can go for R equal to 5. That means you are lowering the force, but you are paying the price by having a more capable engineer to design the building as per the appropriate detailing. Coming to the SA by G, now this is an important factor which we have to understand. SA by G is like the response curve that we study in our basic physics. However, in physics books, you will see the response curve in terms of a frequency, whereas in a building, for convenience, instead of frequency, we talk of time periods, because it turns out to be a more convenient number to work with. But again, if you are going for a machine foundations, you will go back to response spectrum curves which are drawn in terms of frequency. That means you have to keep your mind flexible that whether it is in terms of frequency or whether it is in terms of natural period. This curve for a certain earthquake is very wiggly, but then we say that no, we cannot design with these wiggly curves. Hence, a very smoothened curve has been provided for convenience. Okay, and anyway, it doesn't matter much because finally the building is going into the nonlinear region. Hence, should not be very picky about the wiggly curve, and we can work with a smoothened curve. Now, these 3 lines are for the different types of soil conditions. Now, that means I need to have the geotechnical information to compute this SA by G. Now here comes that for any building, we should have some geotechnical tests. Unfortunately, we will see that many of the times we assume something or we cook up some data, which is definitely not advisable. In our country, we need much more geotechnical investigators than we have at present, who can do, proper geotechnical study. Based on their recommendation only, we can pick up which of these curves, like are we talking about a rock condition or whether it's a medium soil, a soft soil, it depends upon the sheer velocity of the soil layer which is beneath the building. That means given a natural period of a building. Now the code also gives us certain empirical expressions for the natural period. Given the natural period, we go to the curve based on the geotechnical report, and from the curve we go this to the ordinate to read the SA by G value. This is the way we can quickly do it. Now once we have computed the base shear, then we have to distribute the base shear along the height. And that distribution, as per the equivalent static method, is based on what is called the first mode of vibration. First mode of vibration means it's a natural tendency of a building to vibrate, unless the members are in a different type of configuration. Now based on the first mode of vibration, the distribution of the force, this is just like breaking up the force into certain factors. It is a parabolic form, and once I know this force, then from there I do the structural analysis. Coming back to again the stick model, that what are we going to learn at the end of the class today when we do the tutorial? Today we are going to learn that how to compute these lateral forces with which I will be doing the structural analysis. That means first I need to get the seismic zone map, estimate a time period, get the SA by G value, consider some values of I and R, I can compute the base shear. Once I have computed the base shear, I have an expression to distribute the base shear along the height. With the stick model, I can compute what will be the overturning moment based on this distribution. And just like the wind calculations, I would expect you to do it in a tabular form, that for every level you're computing these forces, and then finally you can get the overturning moment. Now, when we are going for the design for earthquake force, it is not just you calculate some force and do the analysis. You have to start with a proper configuration so that your forces are less. And hence there are some guidelines in the code that first of all we should not have unnecessary heavy masses. People are having swimming pools at the top, and you saw in Thailand what has happened. Okay. Integrity of the members, it is not just designing the members, the connections are the most important. That's where Professor Shri will be talking, okay. Especially for precast, that becomes a more consideration. Although we may go for emulative connection, but we have to make sure it is really emulative, okay. Avoidance of large cantilever projections. Unfortunately in our country, if you go to a place like say Ahmedabad, you will see huge cantilevers because people want to take rest in the evening in these cantilevers, okay, in these balconies. Simple and regular configuration of the main structural system. If you start with some irregular configuration, there are some definitions of that in the code, then you are inviting trouble at the beginning. Adequacy of foundations. I cannot overemphasize the importance of foundations. Ductility, that is inherently it has to be there. Providing seismic joints in case if there is some L-shaped in plan, then you have to better to isolate the buildings. And isolation of staircase from the main buildings. If a staircase fails during this 40 to 1 minute shaking, the escape route is lost. And that what exactly happened in Manasi Tower in Ahmedabad, where the building was more or less there, the staircase failed, people were trying to rush down, they got crushed. Earthquake is absolutely unforgiving. Okay. Some other things I will run first now. Robust structural configuration, minimum lateral stiffness, strength. These are ensured by proper analysis, design and detailing. Adequate ductility. What we should avoid is a concept, what we should avoid in configuration is called irregularities. What is meant by irregularity? That there are certain features which can be fine for gravity loads, no issue. But for earthquake, we should not invite it. If we are inviting it, then we have to be very careful. There are broadly two groups of irregularities. Whatever we can study from the plan of a building, it is called plan irregularities, like torsional, re-entrant corners, openings. I'm just skimming through. And whatever we study in the elevation, it is called irregularities in elevation. Okay. One big problem in our country is what is called the soft story because of open ground story. We have a parking issue that we do not have walls in the bottommost story, and that invites trouble. Okay. Now the last part of this presentation is, given that we have these wind forces, we have the earthquake forces, how do we analyze a building? Okay. As a student, at least you should try to learn some hands-on training of our software, because when you're entering for a job interview, the interviewers unfortunately want ready-made products. Okay, you said that we cannot give you ready-made products because different industries have different needs, but some basic idea should be there. Now, whenever you are doing a structural analysis, first it's not that you directly jump into a complete three-dimensional model. No, you can do some preliminary analysis based on even a stick model or a two-dimensional model. It means you select a type of model. And for each direction, if I'm talking of, say, along an X direction or Y direction, I need to calculate the force, wind or earthquake. Then analyze the model. Analysis means we are trying to find out the internal forces, which are the bending moment, shear force and axial force. And we are combining the effects of the gravity load as well as the lateral load. Now these are the load combinations which are specified by the Indian code. The international codes have a bit more specifications, but as I said that if you are, see what may happen is once you graduate from your college, you may be working for some, say, US firm, but working for a Middle East project. Now which code will you follow? It depends. Your mind has to be flexible enough to adopt appropriately. Okay. Now these are the load combinations. Typically you define them within your computational model as per the code that you are following.
So normally for construction projects, the local code.
Yes, unless if the local code is not defining something, then we go to the international code. Like on that day Satya Silan was saying that in case if he's not getting something from here, then he will fall back to the Singapore code, or Singapore code is more like a guidelines. Yeah. Okay. Please note, since both wind and earthquake are reversible in nature, that's why you have to do what is called plus minus type of combinations. That's what it means. And I'm skipping this, that if the earthquake comes from some other direction, then how to handle. Okay. There is something called the square root of the sum of the squares. That means you analyze for X, you analyze for Y, and then try to combine the values, take account of in case the earthquake comes from some other direction, not the orthogonal directions of the building. And there is another called 130 rule. Okay. This is the serviceability limit states. Like we need to also check the drift under unfactored loads to make sure that our damage is limited. Computer-aided analysis, that whenever you have a software, don't use a software like a black box. You should appreciate that there are persons like you who have developed the codes. Hence, you should also do it in a methodical way whenever you are doing a software. The steps are that get the structural system out of a building. The architect will give you a building, functional building. Like this is a complete building, but from there you have to extract this main structural skeleton, which you are going to model. Now, if it is a emulative connection in precast, then the model for cast in place and precast is similar. But if it is a jointed system, then I mentioned on the first day, then you have to be careful how you model the connections. Select member sizes. Typically you select the member sizes based on gravity load criteria. Select the material properties based on what the contractor will be able to supply to you. Once you develop the computational model, you analyze and consolidate and interpret the results. There are certain ways to develop the models. Typically these days, the softwares, they give you certain templates to start with, or you can start from the basic grid line. You have to define the nodes, member sections, boundary conditions, loads, and the load combinations. I will skip these details. What I will do is, see, whenever you are modeling a building, please note it is as good as much as your model. What I mean is, you cannot miss out on very heavy loads. Today, if I am having these steps made up of concrete on a flat, I need to include this superimposed dead load. Today, if I am having heavy brick walls, I need to incorporate that. Hence, that's your responsibility, okay, that you have to include all the heavy loads. And as I said, earthquake especially is very much weight driven, okay. Appropriate live loads and then the lateral loads. There you can also do an analysis for special loads. Now from the analysis, first you have to do some checks. Once you're in a design office, there is no teacher to go through your calculations. You have to do your checks. Even as a research student, you cannot expect that your guide is there to correct your results. No way. You have to check. How do you check? You have to make sure that whatever reactions you are getting under the dead load is more or less close to the estimate of the weight of the building. You're already doing an estimation of the weight of the building while calculating the seismic force. Your analysis should also give that, okay. Similarly, whatever lateral load you're applying and whatever reactions you're getting, the sum total should be equal to the base shear that you have calculated. Then you study the bending moment, shear force, axial force diagrams. That's where you invoke your knowledge from second year, third year to make sure that they make sense. You should have the intuitive feel to appreciate those. Get the envelope diagrams. Envelope means which comes after the load combinations. From there, you pick up the demand values at the critical sections, and also you do the serviceability checks of deflections or drift. You are designing for what is called the demand to capacity ratio should be less than 1. That is a conventional force-based design, that we are picking the force, making sure that the demand is less than the capacity. I will just quickly run through a model. This is like a typical residential building in our country. I'm trying to see the results along one particular frame. This is the model. It looks in elevation. In the gravity load analysis, please note, typically we do not design the floors, or we do not model the floors. We assign the floor loads on the supporting beams. How do we assign? We assign based on what is called the triangular and trapezoidal rule. This we learned in our third year BTech. Okay, that for a rectangular slab, how the load gets transferred to the supporting beams. That's where you are specifying the loads. If there are heavy walls, you have to specify the wall loads. And then you try to understand the bending moment diagram, say under gravity loads. Sagging in the span region, hogging in the support region, does it make sense compared to whatever you have studied earlier? This is the shear force diagram. This is the axial force diagram. As the load is accruing, the axial force is becoming cumulative. Coming to the lateral load analysis, we define what is called center of mass, or to be specific, design center of mass. That means the force is actually distributed throughout the floor area. But for convenience of analysis, we apply the force at a certain node, which is called the design center of mass. I will skip some of the details. This is the tabular form of the results. You have to understand the profile of the forces, how you are applying the force. I will skip this, and this is the bending moment diagram, which is quite different from what we have seen in the gravity load. Okay, here what we see that the points of inflection are somewhere in the middle of the beam and middle of the column, except the ground story columns. This is the shear force diagrams. As we go down, the shear force increases, and the summation of all this shear force for all the frames is equal to the base shear. This is my axial force diagram. Under the lateral load, one side will come under tension, another side will come under compression. More or less, intuitively, it makes sense. Okay, with this, I am ending this presentation. Let me just read out so that it gets internalized for you. It can be observed that the member force diagrams under lateral loads are quite different from the corresponding diagrams under gravity loads. I started this lecture by saying that sometimes people assume that your factors of safety will take care of the lateral forces. No, it will not. Okay, because the force diagrams is different. After the values of an internal action at a section of a member are combined based on the load combinations, the maximum numerical value is selected for design. That means after several combinations, whichever is the maximum and sometimes minimum also, we need to design for. For gravity, say for a beam at the ends, we expect hogging moment. But under lateral forces, under the envelope, there it may have a sagging moment. Then if you are not doing the proper detailing, then we are running into trouble. And please note, all of these are applicable for precast construction. Okay, these are generic. This is nothing to do with cast and place or precast. Whatever I have shown today is same for both.
So if I'm a construction manager,
Yes.
I ask my contractor to provide me both lateral loads and gravity loads, right?
Yes.
Separately.
They have to be, can you repeat the question?
If I'm a construction
Yes,
manager,
yes.
I will ask my contractor to make sure he provides me diagrams on the lateral loads and under gravity.
I would say as a proof checker or plan checker, that's the way I would do. So at first you show me the force diagrams under gravity load, force diagrams under lateral load, and then show me the envelope diagrams under the combined loads, so that I understand what the modeler has done. Okay. A design value including the effect of lateral loads can be substantially high and reverse in sign as compared to that under gravity loads. For example, a section of a beam near the column support may have to be designed for both sagging and hogging moments, which we do not see under gravity loads. Okay, with this I am ending this, and I am just circulating one tutorial. Srihari, can you please circulate? Again, this is just to internalize whatever we have studied. You can start building very regular in plan, not much of an issue in terms of complicacy. It is located in Hyderabad. That means now from the zone map, I can get the value of the Z. From the basic wind speed map, I can get the value of the basic wind speed. Okay. Some of these informations are given. You should be able to see from your third year itself. I am targeting the youngest of the group. At least from third year itself, you know how to compute the self weight. Okay, how to compute the live load, how to compute the superimposed load. Okay, now here these are specified. In real life, actually you have to go to the 875 and find out based on the usage that what live load you should pick up. Sorry. And then, as if the type of soil is given, based on that, I have for a certain time period, I can know the SA by G. This is essentially the response spectrum written in the form of an equation. Now, the first, it says that we need to compute the seismic forces as per the equivalent static method. And these parameters also I have just given, just as some representative numbers. This is my expression for the time period. The time period is primarily affected by the height of the building and the lateral dimension. This is also an empirical relationship. Based for a rectangular type of building, this formula is good enough. Okay. Compared to the time period, and given these values of I, R and Z, I should be able to compute VB, the base shear. And then from the base shear, I can compute the forces at the different levels. That's where and you just have a table to do your calculations. Coming to the wind, again we are following the static method. Once we know the basic wind speed, now these factors I have all deliberately kept all of them 1, just not to confuse it right now. Once you start with this basic calculation, later on you can pick up how to read the code for the different terrain conditions, different heights and all those stuff. And consider this CF, this value I have picked up based on the dimensions of the building, and this is the plan and elevation. That means it's like a square grid. Okay, for wind I know what will be the area of obstruction. This is my elevation. I know the different heights, and hence the geometrical variables are all given. That means you should be able to do this problem. Okay. Any question? Yes.
Your slide you have some peak gust velocity. What
Yes.
is the meaning of what is peak gust velocity?
The peak gust velocity means,
Gust is small, okay.
see, if I see an anemometer reading and velocity, this anemometer reading comes very wiggly. How do you do computations? Then what they do is, first we will do what is called a 3-second average. I'm doing 3-second average. Now the peak gust velocity is defined based on this 3-second average. There what I'm having the maximum. And that too you study this over the record of all the months in a year, over several years, see the distribution, and then you come up with this recommended value in the code.
So do we get that from the windrose diagram?
No, windrose diagram means that's a directionality. This is just a reading in a certain direction. But as I'm saying, there are lots of things to know. I would strongly suggest all the undergraduates to come for postgraduate to gain more confidence. Okay, before you jump into the industry, it is nice to have a master's degree to go to the industry if you want to become a designer. Okay.
So wind load calculations. So which one will be more critical? Wind loads acting exactly perpendicular to side, or quartering loads which are acting 45 degrees to side?
No, see, the idea for both wind and earthquake is that if I have a building like this, say this particular building, I will do one analysis in this direction. I will do analysis in this direction, and then say if a force in a member due to this is say Fx, and the same quantity for the analysis in this direction is Fy, then I take their squares, sum them up and take the square root. This is called the square root of the sum of the squares. Like that we try to address that if now the wind comes in this direction, then this expression will be satisfactory. Okay, that is the idea. Okay. It is just like if you look into electrical engineering, two things out of phase, they will use what is called root mean square. Same idea. Okay. That is, whenever things are not, if you just added fx and fy, that is not appropriate. Okay, that's why this is supposed to be more appropriate. Okay.
In wind load calculation, the force coefficient, they are calculating based on the dimensions and aspect ratio. In that it is showing aspect ratio is infinity.
Yes.
So When it will be.
It is like a very, I mean, whenever it is going outside the chart, then you consider that infinity. That's the idea. Okay. That the chart is given for certain values which we expect. I just gave a quick briefing of wind and earthquake so that you can pick up from there. Okay.
Similarly, the ability ratio also 2:1 it is always we need to take
Yeah, see, this is, I would put the question in a generic way that if the values go outside the chart, then what do I do? Sometimes what happens is this R have asymptotically, it has reached a value, I will be able to pick up the value. Else, if it is not asymptotic, then I may have to do some special study. Okay, then let's wind up now for the lunch, and then we are adjourning back at 2.